Okay, good morning. So, coming back to lecture 8, we'll continue with the basic building blocks of linear algebra and quantum mechanics. And from the next lecture, we'll actually start talking about quantum information science. Maybe give or take one more lecture. So today, let's see some basic blocks, for example, of linear algebra, spectral decomposition. So essentially an operator has a spectral decomposition if it can be written as this particular form. So of course this form assumes no degeneracy. However, if there is a degeneracy, so no degeneracy meaning all eigenvalues are different, lambda j are the eigenvalues. So it can be written as eigenvalue and the projector, where each of j's are the eigenvectors in this case, when there is no degeneracy. This is the spectral decomposition. We are breaking down an operator into its eigenvalues and the projectors on the eigenspace. So this is going to be a rank 1 projector on the eigenspace in case of no degeneracy. And in case you have a degeneracy, I'll just write it down as lambda times some p lambda, where p lambda is the projector on the subspace spanned by eigenvectors with eigenvalue lambda. So, okay, just as a reminder from linear algebra, image I is the subspace spanned by eigenvectors with non-zero eigenvalue. And essentially rank of an operator is the dimension of the image. And null space or the kernel K is the subspace spanned by eigenvectors with 0 as eigenvalue. and I'll also call this the support. This is also called the support, and S, the support and the kernel K are orthogonal. So this is just linear algebra, not very important at this point of time, but I would encourage you guys to go back and revise these concepts. So now, what's the commutator of two operators? Commutator is this structure, very important quantity in quantum mechanics as well as in linear algebra. We'll see that. So by definition, what's a normal operator? So normal operator M is such that its commutator with its conjugate transpose is 0. Now, very close to a normal operator is something called as the Hermitian operator, which is equals to its conjugate transpose. So certainly a Hermitian operator is a normal operator, but it's not the other way around. So why are normal operators important in linear algebra? Well, so there's a theorem that says that an operator has a spectral decomposition if and only if it is normal. Now, the proof is kind of neat and elegant. Let's just go through how do you proceed proving this thing. So, proof. Well, certainly. So, by if and only if means we have to prove it in both directions. Given a spectral decomposition implies the operator is normal, and given this a normal operator implies spectral decomposition. So, one way proof spectral decomposition implies a normal operator is trivial. This is easy. Well, you assume the spectral decomposition of the operator M, and you just also have this guy as M dagger. That's going to be something like this guy, and of course you can prove equals to 0. So this part of the proof is trivial. The other part of the proof is quite elegant, so it's worthwhile going through it. So I'm just going to sketch the proof, sketch of proof, where what are we trying to prove? We are trying to prove that given the operator is normal, which means, well, then it implies that it has a spectral decomposition. So how do we go about proving that? Let's try and play around with this. What does this guy mean? Well, this means essentially, by definition, this guy. Now, let's take the most simplest case, a 2 by 2 matrix. Then M dagger is So what does m dagger minus m dagger m equals to 0 implies? What does it imply? Well, it implies that if you multiply it purely in forms of the matrices, it implies essentially a square plus b square is equals to a square plus c square. Please verify these calculations. And mind you, these are all complex numbers, complex entries. So essentially it implies these two relations over here. So what does it mean? I'll pause here for a minute or 2 minutes. You guys think what's really happening? What does this result actually mean? Meanwhile, I'll get some water. Okay, so back again. So in general, this means, see, this is the length of something. Whenever such a quantity comes, this indicates a length. So in general, it means that the length of nth row, length of the first row, and this is the length of the first column. CD, this is the length of the second row. BD, this is the length of the second column. So length of the nth row is equals to the length of the nth column. Just playing with the definition, that's the insight we get over here. Now, how is it useful? Well, for example, we can write m in form of rows, let's say R1, then m dagger shows up as R1 star, the columns. M can also be written in terms of columns. Then m dagger becomes those columns show up as rows. So in other words, m dagger from this guy becomes R1 square, because R is going to multiply by, this is going to be multiplied by this guy, and some other terms. Also, m dagger m becomes similarly C1 square, the column other terms. And when m dagger is equals to m dagger m, that means that R1 squared is equals to C1 squared, which is exactly what we said earlier. The length of the first row is equals to the length of the first column. So how do we exploit this feature to prove the theorem about spectral decomposition for normal operators? What we do is the following. Uh, let's try to diagonalize M. So for that, let's say we are trying to find the eigenvalues. This is the way you find the eigenvalues of a matrix M minus lambda I. You take the determinant of it. That's going to give you the characteristic polynomial. And well, your fundamental theorem of linear algebra guarantees that such an algebraic equation will have at least one root. So this guy has guarantees that this has one solution, at least one solution. Which implies M has at least one eigenvalue, which also implies that M has at least one eigenvector. Well, think about it why. It's kind of easy, but I'm essentially trying to solve the eigenvalue equation. This is the eigenvector, and having a non-zero eigenvalue guarantees that I have at least one eigenvector. I just am seeking solution to this guy, and so for this to hold, I need one root over here. One non-zero eigenvalue implies that I have a non-zero eigenvector. Now, since I have an eigenvector, let me express M as the following. I am guaranteed one eigenvector, so I'll just write M as that particular eigenvector and another submatrix M prime. This is something which I don't know over here, these entries. But this is the way I can write M, where, well, let me call it, yeah. So where this guy is an eigenvector, is the eigenvector. Okay, so where are we now? I'll again write it down as we don't know these guys, but we know this is the form of M. I have one eigenvector showing up here. Any thoughts? What comes here? What did we say earlier? What do we know about normal operators? Well, we know that the length of the first row equals to the length of the first column. So, in other words, if I had this guy as the first column, then these all guys better be 0. And I have a smaller matrix to work with. So I have broken down M into one first row, first column, where this guy was my eigenvector, I'm reduced with this m prime now. And now our attention is going to be on m prime, but notice we can repeat the same process. We can follow what we did for m prime, the same steps recursively. And once again we'll break down m prime into something over here and m double prime, and that way we'll prove that a normal operator implies that I'll have these eigenvalues in the eigenvectors. So starting from the condition m dagger m minus m dagger implies that there exists a spectral decomposition for all normal operators. This is kind of going to be important for us, so it was nice to go through this sort of a proof. So as we said earlier, Hermitian operators, for example, well, there are special kind of normal operators where H, the Hermitian operator, is equals to its complex conjugate. So one can also show that Hermitian operators are normal operators whose eigenvalues are real. How do you show it? Well, the fact that they are normal operators, there exists a spectral decomposition Now if I use the condition h equals to h dagger, then this will imply that lambda j's have to be real. It's a trivial proof. Why are Hermitian operators important? Well, as you know, by quantum mechanically, what we measure is always going to be an eigenvalue of an Hermitian operator, and all our measurement essentially in physics have to map it onto a number line. This is my number line with 0. So Hermitian operators, or the physical operators which are measurable in quantum mechanics, better be Hermitian. Quantum mechanical observables are Hermitian operators. Okay, the other kind of operators which are going to be useful for us are the unitary operators. Which essentially means u dagger equals to 1, or identity, so u dagger. So essentially unitary operators are normal operators whose eigenvalues are phases. Well, how do you show this? Again, take the spectral decomposition proof. set up a spectral decomposition and then just put the condition u dagger u equals to I equals to u dagger, and then it's a trivial proof. One advice is that try to answer these questions or prove these questions using our bracket formalism. Some essential nice properties of the unitary operator are, for example, so let me call this as the first property. Their eigenvalues are just the phases. Then U preserves the inner product. Also, U takes one orthonormal basis to another orthonormal basis. So when you hit every basis vector of a particular basis set by a unitary matrix, you get another basis, simply because intuitively it's kind of like a rotation preserving the norm of a vector. So the vector remains normalized and they preserve the inner product. So all the normal vectors, all the vectors of a basis set which were perpendicular to each other, retain the same angle, orthonormal basis. So Fj, let's say this is the guy, U, Ej. So in other words, I can also write U as Fj, Ej. This would be a change of basis matrix for changing, going from one basis to the other basis. Okay, so this was some linear algebra which we were planning to. Now where we are next. So now let's tackle another question. Just give me a minute. What else do we want to do over here? Okay, so we've been seeing, we saw Hermitian operators, we saw unitary operators, its various properties. So let's talk about projection operators. So essentially projection operators are Hermitian operators all of whose eigenvalues are 0 or 1. So in other words, Hermitian operator is a projection operator if and only if p square is equals to p. So show that if an operator meets this condition, it's a projection operator and with eigenvalues 0 or 1 essentially. Yeah, there are several ways to do it. Just try a few of them. Okay, so what about functions of operators? So let's say in general my definition of a function which takes a complex input gives me a complex output can be extended to operators. I take an input and I get an output. So for example, what's happening is that let's say I have a function of an operator which takes an input as an operator. What do I get? I have a function, I'll put the spectral decomposition of the operator A inside it. So I have, let's say, I, some sort of a spectral decomposition. And that gives me this guy. So you see what's happening? How am I going to show it, by the way? Well, you can see this automatically. You can expand this operator, whatever this function was, in terms of a series. And what essentially is the take-home message is that when I have a function whose input is an operator, that functional definition goes to the eigenvalue of the operator, and then I have a kind of a spectral decomposition. Of course, this is going to be a sum over here. So this is going to be clear with the help of an example. Let's say I have a unitary operator. We already showed that how for a unitary operator the eigenvalues are the phases. Now we define a Hermitian operator H equals to this guy, where this is the same as this thing. Now u is equals to, if you can look at it, e to the power of iota h. So in some sense, let the function fx be the exponential function iota x. Applying this function on the operator fh, where I have now an input Hermitian operator, I get e to the power of iota h, I recover u. So in other words, the take-home message is that usually I am used to defining functions going from complex numbers to complex numbers, but I can also define functions taking an input of an operator and giving me another operator, some other operator. How do I evaluate that operator? Well, that's kind of easy. What I'm going to do is that the functional value, I'm going to take a spectral decomposition of this guy. And this is nothing but the function part of the operator is going to show up as the function of the eigenvalues of the original operator, and this guy is going to retain the same eigenvectors as the parent operator over here. So try to convince yourself. There are several ways of doing that. I can express, for example, this guy as a power series and show this sort of a result, but I'll give you a homework problem. So on this particular thing. Show this. So for example, there might be several ways of showing this. Yeah, so we'll see that, we'll take up that as a homework problem. Okay, so one important construct is the trace of the operator. So for example, well, so in the previous example, let's say I have sine of an operator x. Well, the power series is going to give me some sort of a series in sine x minus x cubed by 3 factorial, so on and so forth. These are all operators with all spectral decomposition. So I'm going to have this guy as a spectral decomposition minus this guy as another thing, term of a spectral decomposition, which is going to be sum over some eigenvalues times some lambda I, so on and so forth. So ultimately, this is going to be eigenvalues times, I'll collect all the eigenvectors what's going to remain over here collecting all these terms is going to be the sign of the eigenvalues over here, where of course x was so this is sort of an important useful trick we are going to have. The function of an operator turns up into the function of the eigenvalues of the parent operator times the same eigenvectors. Okay, so another important construct is the trace of an operator. So, well, trace of the operator is essentially sum of all the eigenvalues, or in other words, sum of all the also, which is equals to sum of all the diagonal elements. This guy. Some important properties of a trace are trace is linear. Trace of a plus b is equals to trace of a plus trace of b. Basis independence. Trace of a is independent on what basis I am evaluating this matrix. How do I show it? I just Well, again, I stick bunch of identities. Remember the identity operator. I now have it sum over. I stick an identity operator here, ej. So what do I get? I get, I'll write it down again. What I'll do is I'll interchange. These are just two numbers. What happens when I just interchange them? I get and I get so I started with evaluating the trace in some basis ej, which was exactly equivalent to evaluating it in another basis. Also, trace is cyclical. My request is for you guys to play around with these properties yourself, and that way you'll get more accustomed to the bracket formalism. So trace of AB is equals to trace of BA. So which is to say, how do I show this? AB, EJ. Once again, I'm going to stick in a bunch of identities, as you guys have already guessed by now. EJ, A, let me stick an identity over here. So I get FK, FK, B, EJ, and then I swap these two guys. These are just numbers. So which gives me FK, B, EJ, EJ, A, FK. This is going to be FK, BA, FK. So evaluating trace of AB is same as evaluating a trace of BA. You know, this story can go on. Trace of ABC is equals to trace of BCA. Also, what is the trace of this operator? Well, this turns out to be just the inner product, this guy. How do I show it? Well, again, I put an identity, or I express it in terms of some sort of a basis, evaluating that I am evaluating this trace with respect to some basis. I just change them. That's going to give me notice this guy is just the identity. I'm going to remove the identity. I can tack it along the identity anywhere. I can remove the identity. That's going to give me essentially this guy. So essentially the message is that the trace has the tendency to convert the outer product into an inner product. So once again I have trace of some operator, this guy, and it turns out to be, this is going to be equals to over here. How do I do it? I'll again try to evaluate the trace in a particular basis. And I'm going to again remove the identity. Once I remove the identity, I get this guy equals to. Okay, so this essentially was it. I think we've come to the end of this particular class. There's one more small thing which I wanted to discuss was the, maybe we'll take it up the next time, but till then, simultaneous eigenvectors theorem. I'll give you some time to think about it, but essentially this says that two normal operators have simultaneous eigenvectors if and only if they commute. So how are you going to show it? Well, the first part, that if you have simultaneous eigenvectors, and you have to show that the operators commute, well, that's trivial. You take the spectral decomposition and you show that they commute. What about the other part? The other part is, what I mean is that if A commutes with B, then you need to show that A and B have a common set of eigenvectors. So try and show this. It's a very simple, elegant kind of a proof. We'll pick it up, and of course there can be several ways of proving it. We'll see that in the next class.